This is Bob. He's a bacterium. This is Bob's DNA. It has a 5' end and a 3' end. The 5' end is attached to a phosphate, and the 3' end is attached to an OH. The different charges of these groups creates a polarity between nucleic acids. When new DNA is made, it is done towards the 3' direction. Also, DNA is anti-parallel, so the ribose sugars have opposite orientations. This allows for easier complementation and bonding of nucleotide base pairs, as well as better alignment of ribose sugar charges. Now let's take a look at DNA replication. Bob's DNA must be opened for DNA replication to occur. Helicase is on the case. Helicase breaks the hydrogen bonds between nucleotides and opens up the DNA. Gyrase comes in and relieves the stress caused by supercoiling when the DNA is opened. SSBPs are also here. They're proteins that stabilize the single strand and prevent DNA from reverting back to double strands. Now let's start at the origin of replication, where DNA polymerase III can find a free OH group and begin adding nucleotides, elongating the DNA. What if there is no free OH for DNA pol III to attach to? In comes RNA primase, a type of RNA polymerase that can add RNA segments wherever it pleases. RNA primase adds OH to the origin of replication, as well as multiple other locations for the lagging strand. What's a lagging strand? Well, when DNA is opened, a new strand is created that runs opposite of the old strand. If the old strand is being opened towards the 3' end, the new strand will be like this. And in order for synthesis to occur from the 5' end to the 3' end, DNA polymerase III must wait for more DNA to open up. It makes segments called Okazaki fragments. RNA primase sets up primers for DNA polymerase III to follow while making these fragments. Then DNA polymerase I comes in, removes the primers, and replaces them with DNA. However, a little nick is created because it can't fill in the space behind it. But fear not, because ligase fills them in with phosphodiester bonds, connecting the Okazaki fragments. Now say the old DNA strand is opening towards the 5' end. DNA polymerase III can drive into the opening of the replication fork and continuously make DNA without stopping. This is called the leading strand. If DNA polymerase I could not perform its 5' to 3' exonuclease activity, it cannot remove the RNA primers and replace them with DNA. This may cause DNA polymerase to keep going back to the primers and trying to add more nucleotides, stopping replication from progressing. And these are the references.